Now that we've looked at how atoms look when they are single atom Lewis dot structures, let's go ahead and show bonding. Now, this is very rare, but this molecule, HCl, could be described as ionic or covalent. So it's a good one to show the example of the different ways in which you would write an ionic versus a covalent bond using Lewis dots. Remember, in both cases, chlorine was to be 8. Hydrogen is an exception you'll find about soon enough, but it can only fit 2 electrons, so it attempts to reach 2. Almost all of the elements are aiming for 8. It's just that hydrogen's a little bit of an exception. So when they are neutral, hydrogen has 1 dot because it's in this first energy level right here. Chlorine, again, that's 1, 2, 3, 4, 5, 6, 7, 8, and chlorine's in here. So chlorine has 7. 1, 2, 3. You can do this singly. It'd probably be better that way. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to repeat that over here so we can indicate both types of bonds. So for an ionic bond, remember ionic bonds are about transferring electrons. And so what has to happen with the ionic bond is that this electron right here, it has to be transferred to that chlorine atom. So you end up with a total of your 8 electrons around the chlorine, and hydrogen ends up with no electrons. And notice that this is hydrogen plus now, and this is chlorine minus. So now these two ions are attracted to each other because of their positive and their negative charges. Now if we're looking at the covalent bonding, remember this is all about sharing electrons. So it means that this electron and this one, the ones that both have an open spot, they're going to come together into the middle of the molecule and they're going to be shared. I'm going to draw it with 2 dots, and I'm going to go ahead and leave the electrons around the chlorine atom. And then we use lines to represent shared electrons. So I'm going to turn that into a line. And that's our covalent bond right there. So you see the difference in the 2 styles of bonding. So go ahead and draw the molecules as Lewis dot structures. So we have this one and this one. Determine which is covalent and which is ionic first based on the locations on the chart. I'll give you a pause. Pause the video and go ahead and draw those molecules or compounds. You should have gotten that this was covalent and that this was ionic. So when you draw your chlorines, remember there was an extra electron here and like here, and both of them come together to form the bond. So every time we draw a line like this, there are only 2 electrons ever in any little line drawn like this. So those are 2 electrons. Now MgCl2, remember here was Mg, put those little dots in there, and then we had Cl, 1, 2, 3, 4, 5, 6, 7. You should pair them first instead of the way that I'm showing it. Cl, 1, 2, 3, 4, 5, 6, 7. So again, I've got an empty spot here and an empty spot there. So notice my electrons, one's going to go to each spot. So this one will go there, and this one will go there. Now, don't try to figure out exactly where all the electrons will go, because sometimes an element will have a little bit of extra electrons, and it might be willing to give up more than an electron, more than like 1 or 2 electrons. And you don't really want to exactly think of it like that. But the way you would draw it is Mg, 2+, and then you would have chlorine, minus. So let's review this octet rule I keep referring to. The octet rule, it just shows that molecules or ions tend to form compounds, or we could say structures, in which the atoms are surrounded by 8 electrons each. Here's the crazy part. We have some exceptions. So to begin with, we have some issues with hydrogen. We've already said that hydrogen is too small. We've also said, well, we haven't said yet, but we're going to say beryllium is also very, very small. Boron is very, very small. And then beryllium, I know it's on the left-hand side, and it usually does ionic bonding, but it can be used for examples for covalent bonding also. It's kind of a weird little element. So hydrogen, he doesn't form 8. He only forms 2 electrons. That's all he fits around him, which is 1 bond. Kind of like, imagine if you have a marble, how many beach balls can you fit around it? Not very many, because the marble's too small. Beryllium can hold 4 electrons, and that is 2 total bonds. And then boron can hold 6 electrons, which is 3 total bonds. Once we get past beryllium, we're finally large enough to follow the Octet Rule. So all of those atoms will use 8, 8, 8, 8, 8. They all want to get to 8. So does everyone below them, but everyone below them is of a special size. And what that means is that if the molecule kind of forms that has more than 8 in the middle, they're big enough to accommodate it. So it's like they aim for 8, but everything here and down, all of these, they can hold more than 8. There's different words for this. One word is expanded octet. Sometimes this is called being hypervalent. But those atoms can. So the funny part about this is that really there's only 5 elements that absolutely always, every single time, have to have 8. Carbon, nitrogen, oxygen, fluorine, and neon. Again, the other elements are aiming for 8, but they can do more. If it looks like they do, then they will, if a molecule forms. And keep in mind about the 3 ones that cannot quite make 8 electrons. And the question might come up, why do you care about the shape of molecules? Well, here's the thing. We have things like DNA that are very, very bound by shapes. We have things in industry that are very bound by the shapes that they form. So when you want to do a reaction, if you have a molecule that has some things that are going off of the sides of it, but it has empty space on the top and the bottom, that's important to know, because that means that you could have some big molecule come in and attach there or there. If, however, instead of that situation, if you have a carbon and it's all blocked up, it's got some kind of atoms on all the sides of it, there's not room for a big molecule to come in and attach to that carbon. So the shape of the atom, it affects a lot of things. It affects what kind of bonding will take place. It'll affect long-range bonding. So it's really an important topic. So now that you know how to go about drawing these covalent things with lines, we're going to practice. We're going to go with things that are more than 2 atoms. So we're going to do our example with CF4. And we're going to go through step 5. And we actually are going to do step 7 next time. But we're only going to go through step 5. But there's more to it that we'll talk about later. So we're going to add the total number of valence electrons. If the structure has a charge, make sure you add in an electron or so if it's negative. So if it's -1, you would add in 1 electron. If it's a +1, you would subtract 1 electron. But the CF4, it's neutral, so we don't have to worry about that. So, and you'll put a big old box around it. So let's look at CF4. So C and F. And if you can't remember for sure, here's our valence chart right here. So carbon is over here. So carbon has 4 valence electrons. And fluorine has 7 valence electrons times 4. So when you add that up, that's 28 plus 4 is 32. So that's that number that you want to put a box around. So that's pretty simple. And so let's go ahead and look. You'll scroll to the end of this page of notes. You'll see what you want to look at right here, these charts. So since you know that's the first step, let's go ahead and figure out the valence counts for all of these different atoms. So for example, hydrogen has 1 valence electron, and there are 2 of them. So your valence count is 2. Or for beryllium and chlorine, again, this is in the second column. That's in the 7th tall column. And there are 2. So this is 14 plus 2 gives you 16 total. That's what you want to do for all of these elements. So now go ahead and fill them in. And look, there's several of them to practice with. So go ahead and make sure that you get all of those. And I'm going to review what you should have gotten. But go ahead and fill it in yourself.